So that's a lot of what I wanted to show you. The other thing I want to show you, let me see what my values were. I had some values that I was working with earlier that I liked. So I was making that 5, 5, and 1,000. So let's try that. 5, 5, and 1,000 right there for the second delay. And actually, let me make that smaller. There's no need for us to wait around for all that. Let's try these. Okay, and I'm going to scroll back. The output is still running over here, but I just want to show we're generating elements. They're going into step 1 very fast. And they're eventually going into step 2. You can see that 200 millisecond delay over there. So we have, after step 2, entered step 2. And now as we go along, what's going to happen, we can scroll down here just a little ways. So you can see step 1, this is actually the value 23 is going into step 1 and it's coming out as 46. And then the second one here is after step 2, it's working on value 6. Step 1 is working on value 23. So you could see how the buffering is helping. Step 1 can keep working and going up to 23. Even though step 2 is running slower, it's only up to number 6 down here. And that's what the buffering is doing for us, is allowing step 1 to keep working when it's faster than step 2. And it's filling up this buffer right here. And then the other thing I wanted to show here, and remember that a lot of things are happening in parallel here. You can see these workers have all kinds of different numbers, 5, 4, 1, 2, there's 10 over here, 7 right here. A lot of things are happening in parallel, so at times this could be a little bit confusing. But what I wanted to show is that as things are going on, periodically we're generating a new element. So you see here, generating a new element 40, generating a new element 41, a new element 42. So what's going on is that there's some feedback going on here. And as elements come out of this buffer and go into here, this buffer is essentially saying, I'm ready for another value, or I can take another value. And as it takes another value here, then another value goes from this buffer into step 1. And then this buffer can say, hey, I'm ready for another value. So that's when generate element is getting called here, here, and here. And then there's one more interesting thing if I let that run all the way. And I did let that run all the way. So you could see the take is I just wanted to take these number of elements, and that is 20. And you actually see that down here after step 2, the last value is 20. But the other thing that you see is that values are entering step 1 here. So we're up to 37 over here has entered step 1. And then actually even 38 has entered step 1. So even though I'm saying I only want to take 20, like this right here, what happens is the take method counts the 20th element, but two things are going on. First, it takes a little time for its termination signal to propagate back upstream, and during this time, the upstream stages keep producing more elements. And second, the buffers also contain many elements because of the delay times I used. So element 55 has been generated upstream. And I have some notes down here about how take works in ZIO Streams when combined with buffering. So what's happening is buffering creates demand ahead of consumption. So when the stream starts, it creates an initial demand for elements to fill all the buffers in the pipeline. So we have 3 buffers, capacity is 16 in each. So we have a potential for 48 elements being in flight while we're working. The generation stage runs ahead because it's very fast. This is with the 5 millisecond for the generation stage right there. So that's running very fast. And then we jump down here to termination signal propagation. So the take 20 operator counts 20 elements that reach the end of the pipeline. However, it takes time for the termination signal to propagate back upstream. So upstream means going from here back up this way. And then during this time, what happens is that the upstream stages continue producing elements. And then as we read here, when the 20th element completes, a termination signal starts traveling upstream. Elements already in the buffers or pipeline or being processed will continue through the pipeline, and then new element generation eventually stops. But as you saw over here, not immediately. It's already up to 55, even though we only wanted 20 right here. And we have some notes here. In a previous example, I got up to 38 while I was only taking 20. Now we're up to 55. And that has to do with these number values that I'm changing over here, those guys right there. And then the final note here is that this behavior is actually beneficial for performance because it allows the pipeline to maintain high throughput. And it says if you need strict control over exactly how many elements were generated, we could place that take operator earlier in the pipeline. So you might take this take operator right here and move it up to this area right up there. Okay, and then there's actually two other things I wanted to note. So when you look at the buffer documentation right here, it says that it allows a faster producer, like repeat ZIO, to progress independently of a slower consumer by buffering up to capacity elements, that value right there. And one thing it says here is that the combinator destroys the chunking structure and it's recommended to use rechunk afterwards. So I have a note here that we could put rechunk right there. So we talked about chunks inside of here. So what's happening is that the chunk data structure is getting destroyed right here. And then when we call rechunk on this line, we're actually saying go ahead and rebuild that chunk data structure. And in the real world, you may want to use rechunk because you probably won't have known delays like this. Now let's see what that does for us right here. And actually, I'm sorry, let me go back here. Let's make these slower. Make that like 10 seconds right there so we can see what's going on here. Whoop. Okay, and I'll kill that so you can see what's going on is we're generating elements very quickly. And not only do we generate 16, but the rechunk is saying let's go as high as 48 right here. So it's generating elements, putting them in the buffer. Then they're being pulled downstream. So rechunk can handle 32. So there's 32 coming in here. Then there's 16 coming in here. That gets us up to 48. And then what happens is one of these guys entered step 1 right there. One of them went into here. And of course, step 1 is really slow. So that's how we get up to 49. We have 32, 16, and then that one that got in there. So I just wanted to show that because it's in the buffer documentation right here. And in the real world, rechunking is something that you're probably going to want to do. In our situation, it isn't necessary because we have known delays and a really small data set. But in the real world, you may want to use rechunk right there. And you may actually want to do it after each buffer call. And then a really crazy thing is if you use buffer unbounded instead of buffer right here. Now, if we look at the documentation, buffer unbounded says allows a faster producer to progress independently of a slower consumer by buffering chunks into an unbounded queue. So if you wanted to know what an unbounded queue is, let's take a look at that and let's actually clear that and do this. And that, my friends, is an unbounded queue, and I'm going to kill that. So you can see that's an enormous difference, is that generate element is generating new elements every 5 milliseconds. And buffer unbounded is saying, hey, give me all you got. So every time it generates another one, buffer unbounded is like, yep, give me another, give me another, give me another, give me another. And so you could see what happens over here with that one. So we do not want to use buffer unbounded here. There may be real world situations where you want to use it, but I'm not using that here. And let's see if there's anything else I need to show you. So I talked about repeat ZIO. I talked about buffer and the capacity elements. I talked about map ZIO. And I covered how take works over there. And then I have some notes in this section. And I'm going to let you read these on your own. You can get this code over on GitHub. And this was based on these values that I had over here. So the 5.5 and the 1000. And it talks about this demand propagation and how everything works inside of this code right here. So I'm going to go back and change that back to 5, and we'll change that back to, let's say, 1000. And I will try to remember to leave the code just like that on GitHub so you can start from there. So I would encourage you to come in here and take a look at this code, change anything you want, of course. And then a real fun thing, as you just saw, was to change all of these values over here and to see how that affects your output. And in doing that, I think changing these values over here, really any of them, really makes this such an interesting example because you saw how take worked down here, and then of course you saw how the buffering worked over here. So go ahead and grab this code from GitHub and feel free to change anything up here, anything in here. Try buffer unbounded, try rechunk, and see how all of that works for you.